Okay, so this is our review exam that you were supposed to have filled all out, right? Now, if I know you guys, you got it all done and you didn't have any questions. So we're done, right? No? I guess it's still going to labor a little bit to get up, but unfortunately, I usually save it as a PDF file, which will load faster, but I didn't do that today, thinking, it'll be fine. It's still not wanting to load.
Wait, it's coming.
It's coming. Don't give up yet. Is that what you're saying? There. Whew. Okay. So where do you want to start?
11. Yes.
11. Does anybody want one sooner than that?
4.
4. We'll go low bid here.
15.
She already got 4. You're outbid.
Yeah, I just did that.
Just don't forget. Okay, so number 4. Let me zoom this just a little bit.
About 3.
3?
Just do all of them? Yeah. Can we just run through all of it? Yeah.
We don't have time to run through all of it, unfortunately, as much as I would love to. Number 3 says, suppose the study is conducted in a two-tailed hypothesis test of the null hypothesis that the true mean is equal to 4, has a p-value of 0.049. So we have a null hypothesis that the true mean, mu, right? That's our symbol, is equal to 4. And that's our null hypothesis. The p-value is 0.049. So at the alpha equal 0.05 level of significance, what would we conclude? Would we reject the null or not? Yeah. What about at, so I'll write that down. Alpha equal 0.05, reject. What about alpha equal 0.01? Then you would fail to reject, right? Remember that a confidence interval has to make the same conclusion. So a 95% confidence interval would go along with alpha equal 0.05. It would have to reject 4, which means what? Would 4 be in the interval or not in the interval? Not in the interval. So a 95% confidence interval would have to have an interval that excludes 4. So like 4.1 to 6.1 or something like that, right? But a 99% interval, which gets wider, remember, the higher the confidence, the wider it gets, that would need to fail to reject, so it would do what? It would contain 4, so it might go 3.9 to 6.3, something like that. So now, which of these says that? A says a 95% confidence interval would exclude 4, but a 99 interval would contain the number 4. That's what we just said. So A is the right answer. Yep.
So how do you know that 0.05 is reject and 0.01 is fail to reject?
Because the p-value is 0.049. So 0.049, remember how you use a p-value. If the p-value is less than your alpha, then you reject the null, right? And it is less than 0.05, so you're going to reject. But it is bigger than 0.01, so if your alpha was 0.01, you would fail to reject, because you'd be bigger than that. So the intervals have to match that. Okay? Number 4 says, suppose 2 laboratories working independently measure water samples. Lab A collected 150 samples, Lab B 15. So Lab A got 10 times the sample size, right? Both labs did all their work accurately, and both used a 0.05 level of significance to test if the true mean is greater than the acceptable limit. Yet Lab B did not conclude the levels were too high, while Lab A did. Clearly, one of the labs has made the wrong conclusion, making either a type 1 or a type 2 error. Which lab most likely to be the one in error, and which type of error would they have made? Which do you trust the most? Which lab? A, because they got the bigger sample, right? So Lab B probably made a mistake, so I'd say that first. Which lab most likely is the one in error? Lab B. Now, if Lab B made an error, what type of error would it have been? Type 2. They failed to reject the null when the null is probably false, because the better study rejected it, right? So,
You don't like type 1 and type 2?
type 1 error is when you reject the null hypothesis, but the null is actually true. So you falsely reject the null. Then a type 2 error is you falsely fail to reject the null. That's hard to say. Type 2 error is you don't reject the null, but the null is actually false. Right? You should. Yep.
To figure that out, would you use that like square thing that you did?
Yeah, I made a little table, right? And we had decision, so reject and fail to reject. And then up here we said the truth. Null is true. Null is false. If you reject and the null is true, then what kind of error is that? That's type 1. I'm not sure I have it organized exactly the same as before, so don't change your cheat sheet. You're probably okay. And then this one is correct, right? If you reject and the null is false, that's what you want to do. This one is also correct. This one is a type 2 error. And this is the one that B did. They failed to reject, but it's really false. Yep. It says, she asked, how do we know that they failed to reject it? It says, Lab B did not conclude the levels were too high. Right? So that means, think about what the null and alternative hypotheses would have been. The null would be, the alternative would be the levels are too high. So the mean is greater than some limit. Right? So mean greater than, I'll say L for limit. So then the null is less than, so they failed to conclude the limits are too high. They failed to reject the null. Okay? Next question.
11.
Presley had her hand up. She's just quiet in here. What is the next one you want?
6.
6? Okay. Okay, this is referring to the previous question. Let me scroll it back down so that it shows on the camera. So this one is about student mean ACT math scores, and they get, you're supposed to compute the 95% confidence interval. But then in 6 it says, in that previous question, after a student determines the 95% confidence interval, they conclude that that means 95% of Kansas students had a score between the endpoints of that interval. Is that the correct interpretation of a confidence interval? No. What is the correct interpretation? That's right. The correct interpretation is we're 95% confident the population mean is in there, not that individuals are in there. It's not 95% of all individuals. It's 95% confident the mean is in there. Okay? Which one of these is the right interval? I heard A and I heard B. Should we take a vote? I actually don't have a key with me, so I don't remember which it is, but it sounds like everybody's saying it's A. Which function on your calculator do you use to do number 5? T-interval. It's a means problem. There's one sample, so it's T-interval. Okay. All right. And I heard 9. Okay. Number 9 says, in the general U.S. population, it's been reported that 25% of adults smoke. In a recent survey of college students, there were 65 out of 505 subjects that said they smoked. Construct a 99% confidence interval for the true proportion who smoke. And then provide correct interpretation. Okay? You've got your little tree diagram now, right? Ready to go? Is this means or proportions? Proportions. Is it one sample or two? One sample. So, and is it a confidence interval or a hypothesis test? It's a confidence interval. So you're going to use 1 prop z int. Right? So go to 1 prop z int on your calculator. And the first thing that it asks, doggone it, I forgot my calculator again today. The first thing that it asks is x and n, right? So what is x? 65. N is 505. And then it's just the confidence level, right? That's all we need. So confidence level, it says to do 99. So put in 0.99. Calculate, and what do you get? 0903. 1671. Okay? Now it says, provide the correct interpretation of the interval. Your test will be like this. It'll say to do the interval, and then it'll say provide the correct interpretation. And there will be some people that don't read the whole question. And they just give me the numbers, and they don't say what it means. So you miss points if you do that. Right? This problem might be worth 8 points, and you missed 3 because you didn't give an interpretation of it. So what is the interpretation of this?
99% confident that the true population proportion of college kids who smoke lies between that interval.
Okay, very good. We are 99% confident that the true proportion of college students who smoke lies within this interval. Does the interval provide sufficient evidence to conclude the proportion of college students who smoke is different than 0.25? Yes. Why? Because 0.25 is not in here. It doesn't have anything to do with 0. It has to do with 0.25 because that's what they ask about. Right? Since 0.25 is not in this interval, you can say, well, it isn't 0.25. Remember, a confidence interval is the set of all values that are plausible. And this is saying 0.25 is not plausible. What is the margin of error for the interval in part A? How do you do margin of error for a one sample proportions problem?
Take the z critical times the square root of p times 1 minus p over.
Okay? And that's correct, except we don't know what p is. So we have to substitute in p hat. All right? And then z critical value for 99% confidence. You can do inverse norm of what? 0.005. Right? It's half the leftover area, or half of alpha. Right? So if it's 99% confidence, alpha is 0.01. Half of that goes in there. Why do I cut it in half? Because it's two-tailed. It's a confidence interval by definition is two-tailed. It has two ends to it. Right? There are one-sided confidence intervals, but we don't do them in this class. Right? So put that in.
For inverse norm
For confidence intervals, yes. They're not expensive, at least. So the number you get here will have a negative in front of it, but you just ignore the negative, and it's 2.576. Right? So now we multiply that, 2.576 times the square root of p hat, and we don't have p hat. What is p hat? 0.1287. So putting that in here, and divide by n, which was 505, what do you get? 0.0384. Okay. Now, does anybody see a quicker way they could have got that when you already have the confidence interval?
Subtract the mean by.
You know that a confidence interval is the point estimate plus or minus the margin of error. So if you take either end of the interval, it's easiest to take the upper end and subtract off the point estimate. You should get that same number. Okay. And you would. But I want you to know the formula. I may give us a scenario where you don't know the ends of the endpoint. All you know is these pieces. So you need to know the formula. So, yep.
How did you get 0.1287 again?
That's the sample proportion, and that's 65 over 505. Right? It's x over n. And remember, it's possible you'll get a problem like this where they don't give you x, which your calculator wants. They only give you p hat. And then you have to use this relationship to solve for x by multiplying through by n to get that p, to get x rounding to the nearest whole number. All right. Part D, one more part to do here. Suppose some researchers want to repeat this study in a similar population at another university, but they require a margin of error of only 4%. What size sample would they need to have? So they're asking me for a sample size. So on your cheat sheet, you should have two formulas for sample size. Right? One for proportions problems, one for means problems. They're different formulas. They're similar, but they're different. So for proportions problems, what is the formula? P times 1 minus P. Over E, and then they do it like that, right? Okay, and you can have Z squared over E squared either way. Algebraically, it's the same thing. And again, we don't know P, so they're going to do this in a similar population. So if you don't know what P is, you use your best estimate of it, and their best estimate is going to be what we got in our study, which was 0.1287. So you can plug those in, and then they're going to use 99% confidence. Oh, it doesn't say, does it? Yeah, that was a mistake. So we'll assume they're going to use the same confidence level we used. They need to give us that. So the Z is that Z critical value that we computed over there. So that's 2.576. And then over the margin of error, they want their margin of error to be 4%. So do I put 4 there? 0.04. You got to convert to proportions. If you don't, you'll get a really wacky number. Then square that. Does anybody have the answer? Okay, 465 to the nearest whole. Now, our book says don't go to the nearest whole, always go up. Right? So is this one where... Okay.
464.99.
Okay. 464.99, yeah. So 465. But our book says even if it was 465.01, you'd go up to 466. right?
Yeah, I got something different. I got 465.06.
It may have to do with just number of decimal places you're keeping. Did you keep 4? And you keep 3 on this?
Yeah, I used a lot more.
You used a lot more than that. Okay. So,
So with 465, so we ran if it was 465.06.
if it was 465.06, according to our book, you would go up to 466. I'm not going to get picky about that. Some books say go to the nearest, some say go up, and I say if you got a sample size of 465 and you add one more, that's not really going to change things, right? It's not. So be practical here. Now, if you had a sample size of 5, going up to 6 would be a huge difference, right? That's a 1/6 increase in the sample size. But okay. Is that enough on that one? 11? Okay. Can I do you are going to make me do every single one of these, aren't you? Just B, C, and D? Okay, number 10 says, in a local factory they produce breakfast cereals. They are supposed to have 18 ounces. That's what they print on the boxes. And what they want is for the boxes to actually have a little bit more than 18 ounces so that you have a really high probability of not being underweight, right? Because they'll have a random distribution. They take a random sample. Well, let me read the important sentence. It says slightly larger than 18, so they can have a high level of confidence that any randomly selected box will have at least 18 ounces in it. Otherwise, they could be subject to penalties. They take a random sample of 20 boxes and compute the sample mean to be 18.6 and the sample standard deviation to be 2 ounces. Use a hypothesis test to determine if there is sufficient evidence from this sample to conclude that the true mean of all boxes is indeed greater than 18 ounces. Now, I've gotten emails from 4 or 5 people saying, I'm struggling with how to know if it's one-tailed or two-tailed or right-tailed or left-tailed, right? So here's how you figure that out. You read that sentence. That's what I call the key sentence, the one where they say the claim or test if this, right? So they say, determine if there is sufficient evidence. So this is the claim. So your brain should go, ooh, here comes the claim, right? The claim is to conclude that the true mean of all boxes produced is greater than 18. The mean is greater than 18. So let's write that claim with symbols. The mean, what's the symbol? Mu, population mean, is greater than 18. Right? So that is the alternative. So the null is mu is less than or equal to 18. Right? So now, is this a one-tailed test or a two-tailed test? One-tailed. Is it right-tailed or left-tailed? It's right-tailed, because this thing points to the right. Right? But think about drawing a picture of the distribution. Right? Mu greater than 18 is my alternative. The distribution is always drawn as if the null were true. So if the null were true, this would be centered at 18, but I'm going to reject it if I get out too big. So out into the right tail. Right? So it's a right-tailed test. Okay? Yeah?
Just to clarify, my understanding is, though, that you will not ask us if that's a right or left-tailed test
No.
on the exam, correct?
No. I will just expect to see it. This is what I will grade. Right? And I don't care whether you know to call it one-tailed or two-tailed or right-tailed or left-tailed or whatever. What I care is that you can get it into your calculator and you can get the right p-value out of it. And then make the right conclusion. That's what's important. Okay? So, what is step 1? This. Right? So this is step 1. Done. Step 2. Determine the right test to use and check the assumptions to make sure that test is valid. So step 2 is it means or proportions? Means. Is it one sample or two? One. So it's a hypothesis test. One sample means we use t-test. So that tells us what assumptions we need to check. What are the assumptions that for t-test to be valid? Okay, you have to have a random sample. Do we have a random sample?
Yeah.
Yep, random sample of 20 boxes. Okay, then there's only one more assumption for means. You need to have a sample size that's greater than 30 or normally distributed, right? We don't have sample size greater than 30, we got 20. But do we have
Reasonably normally distributed.
boxes are reasonably normally distributed? So assumptions are met. All right? So check the assumptions, random sample, RS, random sample, yes, and normally distributed. On the test, don't just say assumptions are met, because that's a pretty good gamble, right? Most of the time, yeah, they'll be met. But I want to know that you know what the assumptions are. If you just say assumptions are met, I'll say, what assumptions? -2. Right? So you need to write them out and say, oh, it was a random sample, and we did have normally distributed data, or whatever.
Are those the two ones just for all means problems or means intervals tests?
Right. Those are the assumptions for means problems. Now, if it's a two-sample means problem, then it applies to both samples. But other than that,
And then proportions just...
proportions, you have the intermediate one of it has to be a binomial distribution.
Okay.
Right? So you have the random sample, that binomial distribution is met, and then you have a sample size requirement of at least 5 successes and at least 5 failures in both samples if it's a two-sample problem. Okay? So that's number 2. Now what's number 3? Well, I was going to scroll down, but there's no real reason. It just has spaces for you to write step 3 and everything. What do you do on step 3? Use the data into this procedure and get the test statistic and the p-value. So you're going to go to t-test on your calculator. You're going to enter in here on scratch paper. When you go into t-test, first thing it wants to know is mu0. What's mu0? 18, right? The sub-zero, make that connection. Oh, it's a sub-zero because it's the sub-zero hypothesis. And whatever number you have there, that's what goes in there. Don't, I heard somebody throw out 0, right? And you get in the habit of that. A lot of them are 0, but it's not always 0. It's whatever your null hypothesis says. Right? So it's 18 in this case. Another really common mistake is to put the sample mean there instead of the hypothesized mean. But the sample mean comes next. They want x bar equal 18.6, right? Don't ever put the same thing in those two places or you'll get a p-value of 1, right? SX2 in 20. And then we need to choose the alternative, right? So it'll say mu, I think it's a colon, and then a not equal and whatever. And then it has mu0. Well, you just look at your alternative and match that symbol, right? So we want greater than mu0. Select that one. And then calculate, and you should get the test statistic T, which is what? 1.3416. I can look at that before you tell me the p-value and go, we're not going to reject the null hypothesis. How do I know? Well, because that's not a very big number. Test statistic is number of standard errors. You are from the null. 1.3 standard errors, that's not very far out into the tail, so probably not going to reject. But what is the p-value? I heard too many all at once. 0.0978. Okay? So what's the conclusion? Did they tell us what alpha to use? No, I forgot that, didn't I?
Part B later, but that gives
Confidence interval. When in doubt, if I forget to give you alpha, and I do about half the time, just use 0.05, right? Because that's almost always what it is. So since this is greater than alpha equal 0.05, what's the conclusion? Fail to reject. Good. So now, step 4. Our book puts this statement as part of step 4, but I kind of like to keep it separate because a lot of people will then say that and go on to the next problem and think they're done. But this is not the final conclusion. What is the final conclusion? Good. There is not sufficient evidence to conclude, and I'm going to go ... and just say it out loud, but to conclude what? Good. And I was watching your eyes, and that's what I want you to do. What she did was look up here and see what she was supposed to test. The true mean of all boxes produced is indeed greater than 18 ounces. That's the statement that should go down here. Right? And you can just, right off of there, you read the alternative hypothesis. That's the claim you're trying to test. Right? Now, once in a while, they'll ask you to test and they'll give you the null, in which case you need to word the alternative. But you always word the alternative here. Okay? In the context of the problem. Okay, part B is construct a 90% confidence interval for the true mean of all boxes. So, what are you going to use? T-interval this time, not T-test. T-interval. And 90% because this is a one-tailed test, and 90% puts alpha equal 0.05 on each tail, so I wanted to get it to match up right. But I won't go through the whole thing on how you enter the data because it's probably still already in your calculator. What do you get for that interval? 827. 19.373. What do you notice about the number 18? It's in this interval. So you fail to reject the null. Provide the correct interpretation. We are 90% confident that the true population mean is in that interval. From the t-table or calculator, what is the t-critical value used in the interval? And what is the margin of error? Well, what's the t-critical value? For 90% confidence, it's inverse t this time, not inverse norm. So it's inverse t of half the leftover area, half of alpha, right? So alpha is 0.1, half of that is 0.05. And then the degrees of freedom, 19. Okay? And what's that equal? 1.729. Right? I will have t-tables available during the test. I won't bring one for everybody because usually 3/4 of you have it on your calculator and you don't need it. But if you don't, then don't worry. You'll still be able to come up with t-critical value. So then the margin of error is 1.729 times the standard error. And what's the standard error for a mean? Standard deviation over the square root of n. So 2 over the square root of 20 times this, what does that give you?
447. I might have done that.
And what? Say it, Laura. 7732.
Your standard deviation of 2.
Yeah. Yep. Take 2, divide by the square root of 20. Take that answer, multiply by 1.729. And that looks reasonable. Notice that, again, once you already have the interval, the margin of error is half the width of that interval. So you could take 19.373 minus your, I never wrote down x bar, but x bar was 18.6, and you should get the same number. You got what? Does the interval provide sufficient evidence to conclude the mean of all boxes is greater than 18? No, because 18 is in the interval, so are numbers that are less than 8. Right? Compare that conclusion to step 4 in part A. That's the same conclusion. Step 4 says not sufficient evidence to conclude that it's greater than 18. That's what this says also. Not sufficient evidence. Okay. Did somebody ask about this one? Okay. Number 11 says, in our survey, a total of 65 people who exercised and 101 people who did not were surveyed by students in section C. Among the sample of exercisers, 15.38% said they smoked, while among the non-exercisers, 34.65% said they smoked. 34.65% said they smoked. Provide a 95% confidence interval for the true difference. What's the first question you ask? Is this means or proportions? Proportions. Next question. Is this one sample or two? Two. We got two proportions that we're comparing, right? Now, that gets confusing sometimes because we did one a minute ago when it says in the general population, 25% of people say they, does it smoke? I don't remember. 25%, and people think, well, there's one proportion I'm comparing to another one. But that one, they don't give us a sample that it came from. They're just saying that's what it is. So that's a population value. But here, they're saying we have a sample of exercisers and a sample of non-exercisers. Two samples. Now, are they independent or dependent? That's the next question you ask when it's a two-sample problem. Are they independent samples or dependent samples? Independent. How do you know? What'd you say, Haley?
They don't affect each other.
Okay, they don't affect each other. That's right. You're not measuring the same people twice, right? That's almost always what it is if they're paired. So it's proportions, two samples, independent. So what's the function you use? 2 prop z int. Okay, so let's write down what they gave us as we come to it. A total of 65 people who exercised. So if I call that sample 1, exercise, they just gave me n as 65. And then they say 101 did not exercise. So non-exercisers, we'll call that sample 2. That n is 101. Next number I come to, among the sample of exercisers, 15.38% said they smoked. What are they giving me? Right, they're not giving me x. That's not x. That's what? The proportion in the sample, which we denote as p hat. So they gave me p hat. As a proportion, I move the decimal 0.1538. So to get x, what do I need to do? Multiply that by the sample size and then round to the nearest whole. And I forgot to put the little subscripts of 1s on those because they're coming from the first sample. So I'll do that. What is this number? Rounded is 10. Okay? And then for the non-exercise, P hat 2 is 0.3465. So then X2 is 0.3465 times 101, which is rounded to the nearest whole, 35. Good. So now you've got the 4 numbers that you need to enter into your calculator into 2 prop z int. Okay? So you'll enter x1 as 10, n1 is 65. x2 is 35, n2 is 101. And then confidence level is 0.95. And then I think that's all you got to do, right? Hit calculate. So what is the interval? Like that. Okay. Wait. And interpret the interval. Interpret that interval for me. Perfect. And the word I was listening for is difference. Right? So we are 95% confident that the true difference in proportion who exercise, or is it smoke? So proportion who smoke among exercisers and non-exercisers, the difference falls in that interval. Right? If you don't put the difference, you're saying, well, I think the proportion is in this interval. Well, those are negative numbers. You can't have a negative proportion. Right? Okay? And then it's probably going to ask if this is sufficient evidence of a difference. Do the results in the confidence interval indicate there is a significant difference? If there's no difference, the difference would be 0. 0 is not plausible according to this interval because 0 is excluded. So the answer is yes. It provides sufficient evidence of a significant difference because 0 is excluded from the interval. Okay, I won't take the time to do the hypothesis test and all 4 steps. It's going to make the same conclusion, which is to reject the null hypothesis of 0. What function would you use on your calculator to do it? 2 prop z test. Same thing, but test instead of int. Okay? Since I've only got a few minutes left, I want to...
Is 15 good?
I don't know. Let's talk about it. We don't have time to work these problems, but let's go through and talk about what would you do on each of these problems. So this one says, this might look familiar to you, 12 subjects are asked to test their grip strength on each of 2 consecutive weeks, where strength was measured by squeezing pressure. During one of the tests, they wear headphones playing classical. The other one, they listen to rock and roll. The order they hear the different music types was determined at random. Is this a means problem or a proportions problem? It's a means problem. Is it 1 sample or 2? 2. Are those samples paired or independent? Paired. How do you tell? It's the same people being tested twice. And the order they hear the music is in random order, right? So paired, so what do you do? Okay, it's a confidence interval, so T interval on the differences. So why did they give us all this? To trick you. That's right. To see if I could bait you into doing a 2-samp T int, which would be wrong. Right? So I want to test whether you know how to do differences, but I didn't want you to have to enter 12 numbers for the rock and roll, 12 numbers for the classical, and then, so I'm trying to save a little bit of time, but just enter the differences into T interval. Okay?
What's part B is this? The design of the study.
Oh, the design of the study. If all subjects receive what? Cross something. Yeah. Cross. No. I heard every cross but the right one. What did you say? Crossover. It is a crossover design. Right? Cross-sectional is different. That's a survey kind of thing. But, right? Yeah.
So did you know to do the T interval on the difference because it asks for the true difference?
No. The very next problem will ask that same thing. I knew to use T interval on differences because I figured out, oh, this is paired data.
So like if we follow that tree diagram, we basically know like what.
Yeah. The third question that you would ask, you'd ask means, you'd ask one sample or two, and then if it's two, you then ask, is this paired data or is it independent data? And that's where you branch off and say, oh, it's T interval on the differences. It's paired data, T interval on the differences. Okay? All right, let's look at 16. 16 says, captopril is a drug designed to lower systolic blood pressure. When the drug was tested, 10 subjects were randomly chosen to receive placebo, and another 10 were randomly chosen to receive active drug. All right, and then we're supposed to do a hypothesis test to see if it's effective in lowering blood pressure. Means or proportions? Means. One sample or two? Two. Independent or paired? This one, they're independent. How do you know? Because it's 10 subjects got placebo and another 10 got active. It's not a crossover design. Right? So you're going to do what function? 2 SAMP-T test. Which of these numbers do you use? Not the differences. You're going to use N1, X bar 1, and S1, and then N2, X bar 2, and S2, and you're going to ignore the differences. Again, the differences is only there to see if you will bite on paired data. Right? So that's the only way I have to test whether you know how to choose or not the right procedure is to give you everything you need for whichever one you choose. Right? So, okay, that's it. We're out of time. So,
the very last part of that one, on part B, go up, down, sorry. Provide 95% confidence interval on the difference. Is that when you do the difference?
No.
You still do the
Yeah, the difference is still X bar 1 minus X bar 2. Right? It's 2 SAMP-T in. Yeah, the word difference is not a tip-off for paired data or not paired data. Right? That's a common way of thinking of it, but that's wrong. So, all right, good luck. Let me know if you have questions as you're studying, and I'll help you through them. Yes, I'll post the key to this sometime today.